All right. Well, yeah, apologies for the technical delays, folks. Welcome everyone to like another episode of GPU Mode. As part of like our distributed lecture series, like I'm really thrilled to have both like Roberto from and Andrei from the ISTA lab in Austria. For those of you that aren't aware, this is a lab that tends to like consistently publish like some of the most interesting like low bit and sparsity work. So if you're in the know, you should know. And I'm really thrilled to have them today talk about like a result that I think made the rounds on Twitter like a couple of weeks back, which is Quartet, which is on how native FP4 training can be optimal for large language models. So yeah, without further ado, Roberto and Andrei, it's awesome to have you.
Yes, thank you for inviting us, and thank you for the warm introduction. And yes, without further ado, let us get into the discussion about how native FP4 training can be optimal. What do we even mean by this? And to start it off, we'll have to discuss how models are trained to begin with. And when we talk about machine learning models, we usually mean it as some sort of parametric functions that are trained to optimize, that are optimized over some sort of objective. And with this optimization, we usually use some sort of gradient-based methods, either like gradient descent, stochastic gradient descent, Adams, SOAP, Muon, or any other fancy kind of optimizers. But in its core, what those methods need to optimize this parametric function is to be able to calculate a gradient with respect to these function parameters of some loss function. And as such, naturally, these parameters are used as real numbers because real numbers parametric functions can be made differentiable, and it's easy and straightforward to apply gradient steps to those real parameters. But in real life, we cannot represent real numbers because it's an infinite set, so we have to use some sort of approximations to be able to numerically represent them inside the computer. And what people usually use to represent real numbers is the floating point numbers, which is an approximation that consists of two parts, a mantissa, an exponent, and also a sign that encodes a very wide range of real numbers, maybe from like trillions from e to the power, from 10 to the power of 38 to 10 to the power of minus 38, with accuracy as high as 10 decimal points. And as such, it makes for good approximations for real numbers because it both has an extremely wide range, meaning that it will probably never overflow on normal operations on numbers that are within some reasonable range. And it also has accuracy high enough such that when adding two of those numbers, the result would be pretty much also a good approximation for the addition of those two numbers. And generally, you can count on any operations on them, such as matrix multiplications, normalizations, attention operation, or applying the gradient step on those numbers to give a very good approximation of what real number would do. That's why they're used for training machine learning models, and they're used as some parametric representations of parameters of machine learning models. But one thing we know from some theoretical results, specifically on large language models analysis, we know that their capacity in terms of how much actual knowledge they can store inside of their parameters that are being optimized, that are being stored as high precision floating point numbers. We know that it's usually closer to 1 or 2 bit per parameter, meaning that the real amount of knowledge that these models can encode into their parameter is much, much lower than the data type that's used to optimize them, these high precision floating point numbers. And this creates some sort of discrepancy between the optimization procedures that we use and the end result that we get, with the optimization procedure using very expensive, very high bit width and high precision floating point numbers, and the end results being that not nearly as much information is being encoded into them. And as such, people have been experimenting extensively with alternative data types that are somehow more rough, more basic, more rough approximations of real numbers that have way lower bit width, but might possibly still allow for efficient information encoding and, more importantly, for efficient optimization procedures to be performed on them and for machine learning models to be trained in those data types. And naturally, the simplest of those representations would be just some fixed subsets of real numbers that would be much smaller than the entire range and accuracy covered by high precision floating point numbers, but maybe it can still allow for efficient training and information encoding into these numbers for their use in machine learning. And let's take a look at some low precision data types that have been used recently by different companies and different accelerators. For example, Apple with their latest iPhone and iPad chips include not only high precision FP32 numbers, but now standard half precision BF16 numbers and the integer 8 numbers as well. And when I say that they included them, it's not only that you can store them in memory, because you can pretty much store any bit sequence in memory, but more importantly, they provide a kernel support for these numbers, allowing for their efficient use in machine learning models for metrics and operations, and for efficient encoding and decoding as well. And if we take a look at Qualcomm recent processors, they took a slightly different approach, where instead of BF16, they used normal FP16, and instead of integer 8, they used unsigned integers. And in general, this trend has become somewhat complicated in recent years, especially from NVIDIA's side, where not only they include the FP32, 16, 8, and even 4-bit floating point numbers, but they also include bfloat numbers and even some integer numbers. And they often add or drop support for some of those data types, and as such, there exists a need for a more robust framework for comparing machine learning training schemes to be used over those low precision data types, to be able to tell more accurately which precisions work best and the trade-offs that these precisions create for low precision machine learning training. And as I already mentioned, these precisions aren't just a way to store data on device, but rather hardware supported precisions for operations that are often used in machine learning. More specifically, the majority of support for these low precision data types comes from matrix multiplication operations, because these operations usually constitute the majority of computations inside neural networks, and as such, supporting matrix multiplications effectively allows you to run almost the entire model in low precision. And this is what we'll be focusing on in this work, that is quantizing the matrix multiplications operations, that is linear layers inside large language models, to try and show that lower precision can lead to better accuracy to speed trade-offs, with the speed theoretically be as high as proportionally faster than higher precision data types. That is, FP4 can in theory be as fast as 4x faster than FP16 or 2x faster as FP8. But those speedups come at a cost of decreased accuracy. More specifically, it has been shown numerous times that as you lower the model training precision, you start losing accuracy at some point, and you can see it on this plot, that as you decrease the accuracy jump in between the curves start to rise up, meaning that the final loss of model strength and that precision starts to become higher, meaning that we lose some sort of model capacity or model capability as we decrease the precision in which these models are being trained in. And this creates a trade-off between the accuracy that we lose when we decrease precision and the speed up that we can gain from lower precision from the hardware supported lower precision data types that can lead up to theoretical speedups, but in practice it depends more on the concrete setup that you're running your model with. And let's start with describing the accuracy. And in general, the simplest thing that we might want to do when designing a low precision training method, the simplest way we can demonstrate its optimality is just to demonstrate that it loses no accuracy while providing speedups. And in practice, many of the recent papers that proposed new low precision training methods showed exactly that, where they just aimed to show that they almost don't lose any precision or don't lose any significant how much they lose isn't statistically significant, or much less than you would lose from otherwise small perturbations in your data or whatever. And at the same time, they show that they can get some speed up. For example, logarithmic and bias quantization only shown like a few percent drop on accuracy on various tasks, while saying that they can get some speedups from lower precision. The leverage score sampling from training transformers with integers said that they have competitive accuracy on a wide range of tasks while showing a real speed up of around 30% over higher precisions. Jetfire also said that they incur no degradation whatsoever while demonstrating some end-to-end speed up. And of the more recent methods, Halo also mainly stated that they have close to baseline accuracy while showing some real speedups. And in general, this is one of the two easy comparisons you can make when comparing inside this trade-off, because the basic win condition for this trade-off is that your method is faster but has exactly the same accuracy, which I've been showing for a few slides, where they mostly claim that they fully recover the model performance while providing some speedups. Or other win condition could be that it has identical or faster speed while having better quality, which is somewhat hard when compared against the baseline, because one would expect that you cannot beat a non-quantized baseline with any training, with any quantized training method. And please correct me if I'm wrong, because to the best of my knowledge, there aren't any methods of quantized training that can be that quantized baseline. And there's a problem with this comparison that, first of all, it's based on a very specific setup, in a sense that in these papers, the authors usually train a specific model, measure a bunch of tasks for it, show small degradation on all of them, and claim that they almost don't lose anything. And they provide speedups for these specific models and say that the speedups basically come for free when using low precision training. But in practice, it doesn't answer any questions with regard to what would happen if you, for example, increased the model twice in size. How would your accuracy drop change? How would your speedup change? And to provide these more specific comparisons, you would need to somehow aggregate the information about both the performance and the speeds between different speedups and make a comparison that would take both the accuracy and the speed into account. And as such, a new model is needed to build these comparisons. And yes, what we would want from our comparison model is to be able to first compare using information from many different training runs to be able to more robustly estimate the actual drops that you're getting. We want to also be able to use this comparison model to extrapolate for the setups that we haven't tested. For example, what would happen if we scale the model 10x in size? What would our findings still hold? And this is very useful because if your model is robust, this extrapolation, you could use it to predict which precision would be better before you actually train the model, to kind of pick the optimal training hyperparameters before actually training the largest model you can to more efficiently utilize compute. And you want this comparison model to also very accurately describe the accuracy speed trade-off for different setups, for different model sizes, and for slightly different methods that provide different kinds of speedups. For example, like forward quantization, which can be done in one precision, providing certain speedup, and backward quantization, which can be done in the same or different precision, providing different speedup. And let's start building this comparison model. And to start with, let us first learn how to compare accuracies in a more robust ways. And to do this, we employ scaling laws. And when we say scaling laws, it means that if your training setup in a broad sense, like a family of models, for example, that depends on the model size and the amount of data that it's been trained on, has consistent performance with respect to those hyperparameters, meaning that it has sort of predictable loss after training for a specific model size and token count. What you can try to do is you can try to fit this predictable loss as a parametric function of your model parameters. For example, a very famous example of a scaling law for LLMs is the scaling law of Hoffman and co-authors, where they predicted the validation loss as a function of model parameter count and the number of tokens it's been trained in, to where they utilized this form that decoupled the parameter count of the model term from the data term, And this scaling law has been validated numerous times in the literature and reused for different purposes, from compute optimal training to comparing to deriving some data saturation thresholds, and generally providing better intuitive for which setups would make more sense after under different constraints. And we can extrapolate this idea to include precisions into the equation, and this is the scaling law that we used in the end for our own description of quantized training performance as a function of parameter count D on number of tokens LLMs were trained on parameter count N, number of tokens D, forward precision P for a certain training method, and backward precision P backward for a certain training method. And let's break down the scaling law. So first of all, it's sort of similar to the previous law of Hoffman and Kothras in the sense that the parameter count and the data coefficients are still somewhat decoupled and only interact with each other through this additional constant gamma. And if we look in more detail into what's happening here, then we can see that the forward precision here affects the parameter count, and only the parameter count, as a sort of multiplicative factor on the parameter count. And naturally, since quantized training cannot outperform the baseline full precision training, this effective multiplier is between 0 and 1. And it falls in line with a lot of previous work that modeled the impact of quantization on training in a similar way as a multiplicative factor. And it also checks out with the observed losses. So this is more like an existing, more like an already existing way to modify the scaling law to include the forward pass quantization. The other part of the scaling law that we see that actually encodes the information about the backward pass is the effective multiplier on the number of tokens. Here we choose to again decouple it from the parameter count, from the simple idea that if your model was trained to saturations, then from optimization theory, we sort of know that backward pass quantization only doesn't necessarily include any consistent biases into your optimization method, but rather just makes your gradient estimation procedure a little more noisy. And from the optimization theory literature, we know that under this noise, the optimization problem, the convergence can still occur to the same loss, but it would be lower for noisier gradient estimations. And from the scaling law proposed here, you can see that the effective multiplier on the number of tokens doesn't change which loss the models, the quantized and non-quantized backward pass models would converge to, but rather only changes the convergence speed. And again, we see that it checks out with the data that we observed, where we see that the gap between the forward pass, the quantized and non-quantized backward pass closes as we increase the data saturation, meaning that as we train for longer. Here we can see it as the gaps between adjacent lines on this plot that become closer together. And as such, from comparing for a single setup, we now can compare for a whole family of models trained for different durations. And from the form of this scaling law, we can see that we can compare different methods with it by simply comparing the effectiveness factors, meaning that if one method has both better forward effectiveness factor and backward effectiveness factor, that is the parameter count multiplier and the data amount multiplier are higher for this method, then this method would produce slower loss across the setups, and we could say that it's better in terms of quality. But again, it's not only about quality, it's also about the speed ups. And if let's think about how we can take speed ups into account. So one thing we should start from is the idea that speed ups for forward and backward pass are not made equal, in the sense that forward pass predominantly affects the inference of a quantized model, in the sense that during training, quantization of the forward pass only affects one of the 3 gems for every linear layer. But for inference, all of the gems are quantized for a quantized forward pass. Backward pass, on the contrary, mainly affects training, meaning that if we quantize 2 out of 3 gems during the training on the backward pass, we would obtain faster training, but it would have no effect on inference whatsoever after the model has been trained. And here we can see a simple table that shows what the forward, backward, and training pass would be under an ideal model. If going from FP4 to FP8 was a 2x speed up, and for a certain forward pass, backward pass precision, what would be the speed up of this mixed scheme compared to FP8? And you can see that quantizing just the forward pass mostly affects inference, quantizing just the backward pass mostly affects training, and quantizing both affects both. And with this in mind, we arrive to idea that we have a separate notion of inference costs for a model and a training cost for a model. And quantization schemes can affect those in different ways. And let's try to formulate this idea about a cost. So let us pick some baseline precision. And for a baseline precision, under fixed precision, a way to characterize the inference cost would be the parameter count of the model, because naturally the parameter, both the compute for a forward pass, meaning for inference, and the memory movement for forward pass for inference is proportional to the parameter count. And as such, you can easily linearly characterize inference budget, in a sense, as the parameter count in some baseline precision. And to account for the fact that different precision can have some sort of inference speedup, denoted as P forward here, to the baseline, to have an inference cost normalized model in a different precision, you can pick the parameter count that would be proportional to the speedup, meaning that if your data type is 2x faster, and you want to have a model that runs at the same inference cost as model with nmax parameters in baseline, you can pick a model with 2 times more parameters with 2x faster data type, arriving at exactly the same inference speed. You can apply the same idea to training cost, which is proportional to both the number of tokens the model is trained on and the number of parameters. And here normalization is a little more complex, because you have to normalize by both training and inference speedup because of the changes in the parameter count again. But with this, you can conduct easy cost comparisons, meaning that you can compare different precisions such that their both inference cost and training cost are the same. And then you can account for the loss in the accuracy via this plugin, these precisions, which would yield certain effectiveness parameter counts, effectiveness multipliers in the scaling loss. And thus, this formula constitutes both inference and training compute normalized comparison for different precisions. And the way we use it is as follows. So we have a bunch of precisions we want to compare. We fit the scaling law for all of them. Then we pick a baseline precision, and we benchmark the speedups of every other quantization method against this baseline method. Then we, for basically any training and inference cost, that we can, for example, parameterize by the parameter count of the baseline model and the data saturation ratio of the baseline model, because these are 2 functionally independent variables that still encode kind of both the inference and run and training cost. And then for each of those, each point in the grid, we can actually predict a loss with the fitted scaling loss. And we can pick the lowest one to say which precision, which exact training scheme would be the best for given inference and training computes. And we can actually plot it like this. As you can see on this plot, we have the parameter count of the baseline model on the y-axis going from 100 million to 100 billion transformer model parameters. And the data saturation is going from around 20, around chinchilla optimal, to around a little more than 1,000, way beyond the chinchilla optimal training duration, almost to data saturation. And here we compare 4 different training schemes. That is the baseline FP8 training, the forward only FP4 training, meaning that we only quantize forward pass to FP4 and backward is still FP8. The forward pass FP8, backward FP4 training, and the full FP4 training. And on the plot on the right, you can see these regions plotted under the real measured speedups for the kernels that we produced, meaning that these regions show under real world inference speed, which compute cost normalized method would produce better accuracy under certain compute constraints. And you can see that we plotted some of the models that have been published recently, such as Lemma 3 or Qwen 2.5 or Gemma 3 on this plot. And we can see that many of them fall inside the regions that are either FP4 for the forward only quantized or full FP4 quantization. And this is why we claim that FP4 can be optimal for LLM pre-training, because some of the models that make sense in practice and that people have trained fall into the region where they would have yielded better loss if they were trained fully in FP4, or at least that's what we predict from the scalar loss and the speedups that we obtained. And this comparison scheme, I just demonstrated that we can use it to compare real kernels for LLM pre-training with scalar loss fitted on LLM pre-training. And we can map out real pre-trained models on the obtained regions to demonstrate the usability of certain precisions in certain training regimes. But in general, this comparison schema allows us to conduct scaling loss-based budget normalized comparison for a very compute-specific setups. And to maybe describe how we can actually apply this scheme even further, is that we had this notion of better effectiveness, meaning that the method is better under fixed, which is true under fixed inference budget. And in general, what it can fixed inference, under fixed compute budget. And what we can say even further is that methods that run in the same precision usually have either identical or very similar compute budget, because they utilize the same data types and in general very similar kernels. Meaning that if we wanted to design a method which is the best for a fixed precision, we can use those effectiveness factors directly to compare methods. And this is what we did in our papers. So the third ingredient of our QAT method is that we use these scalar coefficients directly to pick the optimal backward pass and forward pass schemes. And to not go into too much details here, we compared a number of schemes such as stochastic rounding for unbiased backward pass gradient estimation, EBSMAX rounding scheme, and Quest standard deviation based rounding schemes from our recent previous papers of ours. And here we can see that the stochastic rounding yielded the best performance for the backward pass, and Quest yielded the best performance for forward pass. And I think I'll skip a little about the background. I'll just mention that Quest is a method from the previous paper of ours, which uses standard deviation-based scaling and Hadamard transforms for normalization. And the unbiased XFP4 backward pass method we used was actually originally proposed by Albert Senk and co-authors. And it also utilizes the Hadamard transform and stochastic rounding to produce unbiased gradient estimations. And the whole algorithm looks like this. So in the forward pass, we do the Quest rounding as well as some clipping of the values. And on the backward pass, we do additional Hadamard transforms for gradient normalization. We perform the matrix multiplication lower precision, but then we have to do a number of additional operations like masking and inverse Hadamard's transforms to obtain unbiased and accurate gradient estimations. And with this, you can see already how complicated this method is. And since the optimality regions that I showed before depend not only on the accuracy of your method, but the speedups, the fourth and arguably one of the most important parts of our paper is the kernels that we provide to actually allow this method to be optimal. And here, Roberto takes stage to describe the kernels that we wrote.
Okay.
Sorry, folks. Just before Roberto goes, I had a couple of questions, and the folks from chat have a couple of questions. I think. Maybe
sure. Yeah, I think now would be a good time to answer them. Yes. Yeah, please go ahead.
All right. Okay. So first thing, sorry, this is like a very noob question, but like in some of your slides, you had something like SPFW. What does SP stand for?
So SP just means speed up. Let me find.
Oh, speed up.
Yes. Okay. So here you can even see it in this table. So you have forward inference speed up that we call SP forward, and backward speed up SP backward, and training speed up SPTR. Yeah. So basically we need these speed ups to normalize the compute cost to obtain kind of the real parameter count from some normalized compute costs that take speedups into account.
All right. Another question, which was like about a year back, around the time when Llama 3 came out, I remember a lot of labs had trouble doing post-training quantization on it because, and part of the argument I read was something along the lines of the model is over-parametrized because there's a lot of data, and so if you quantize it, like it just like forgets everything. And then people were predicting the death of quantization. I'm sort of curious, like with the benefit of hindsight, what do you think about this argument now, and like which parts of it were correct?
So I think in general, this argument is very much orthogonal to what we're doing here, because what people described back then was post-training quantization, which is some sort of operation you perform on already trained model. And yes, people have demonstrated that the more trained your model is, the harder it is to quantize in a sense. And it sort of makes sense because the more trained your model is, the more information you've packed onto it, but also it converts to a more stable equilibrium of some sort. And that's why quantization, which is naturally some sort of perturbation on top of your already trained model, would make you lose more information. And here what we'll do is somewhat orthogonal, because here we're training this quantized representation from the start. And what we observe is that we don't see this effect, and the performance is pretty consistent with how long you train.
But there does seem to be some strong relationship here, because like one thing you mentioned was like basically information per parameter. So like if you're training in FP4, then there's less information per parameter. So then when you're doing inference in FP4, you've lost less information. And so like there is some sort of, I think, relationship in your arguments, I feel.
Let me think about it. So the lemma model was trained in higher precision and still encoded some, as people somewhat shown, lower information like the amount of information per parameter for lemma was still pretty low. But probably the representations that you obtained somewhat overtuned to the data type that you were using. So the model sort of encoded slightly more information of it, but still way less than what you're quantizing it to. But by encoding more information, it became more fragile in a sense to these post-training perturbations. And I'm not that familiar with the literature that tries to quantify how much information exactly you lose with post-training quantization. In general, it correlates a lot with additional things people have observed, like the existence of outliers in neural network, which is very hard to combine with quantization, both conceptually and in practice. And I think this is a somewhat orthogonal research direction of how you can quantize to not break down existing models versus actually training quantized models from the start.
All right, then last question. I see a couple more questions in chat. Maybe we'll save them until the end. So I was wondering if you could go to your pseudocode again, like the algorithm code near the end of your slide.
Sure. Give me a second. Yeah, here it is.
So sorry, just like just basics, like what is Quest rounding exactly, and why do a lot of quantization people love the Hadamard transform? I was wondering if you could spell that out a bit
So
more.
Quest rounding is basically rounding. I think it's better explained by this slide. So it's rounding as such to minimize quadratic error over a normal distribution. So it's standard deviation based scaling that was the optimized basically quadratic error. And this is also an answer to the question about the Hadamard transform, because the Hadamard transform acts as a normalizer on your distribution. So the Hadamard transform makes your distribution Gaussian, and the rounding is chosen as to minimize the quadratic error over this distribution. So this is
I
the
see.
basic idea of Quest.
Okay, everything makes sense. Okay, thank you, Andrei, and I guess Roberto, please go.
Okay, can you switch to my screen maybe? Okay, thank you. Yeah, so in this second part of the presentation, I'm going to cover the fourth and last ingredient of our recipe, which is related to CUDA kernels. That basically is we have invested a lot of time and we continue to invest a lot of time here because as Andrei mentioned, the real speed ups of our kernels are going to shape the optimality regions of our method over here. So the better the speed ups, the larger this optimal region is going to be, and the more models are going to fall in this optimality region. So that's the reason why we continue working on them to optimize them further. So before starting with the kernel details, I'm going to give a brief overview of some details that I will refer to in the following slide. So we will just refresh this information. So when we refer to MXFP4, this MXFP4 type, which is the FP4 type that we have used in our Quartet paper, basically that means that we have our values represented by this E2M1 format, and that means that we have 1 bit related to the sign, and then 2 bits for the exponent and 1 bit for the mantissa. And then if this matrix on the middle is our matrix, for each column, each group of 32 elements is going to be assigned to a scaling factor. And this scaling factor is, for this MXFP4 format, is represented by an FP8 value with this representation of E8M0, and that means that 8 exponent, the exponent is basically represented by this, all the 8 bits are represented by exponent values. So in this way, in this new Blackwell architecture, we have hardware support to execute this kind of operation, where for a specific A matrix and B matrix, as matrices to be multiplied, are going to be additionally represented by a metadata information, which are these scaling factors. And this scaling factor is applied to the inner dimension of the matmul. So for instance, for this A matrix over here, the K dimension is going to be divided by 32 in the case of MXFP4, because we assign a single scaling factor to each 32 elements, right? For MBFP4, that will be 16, but that's not the target of this presentation or paper. So let's continue with MXFP4, remembering that we group 32 elements, right? So in terms of hardware, that means that we are going to have 2 matrices, and in tensor cores, we can execute this matrix multiplication with 1 new instruction, which is going to receive not only the input matrices, but also this metadata information, and to produce this output matrix, right? So one of the points that Andrei already highlighted is the impact of the matmuls in this large language model. So most of the runtime of these models is represented by these matrix multiplications in linear layers. So that means that they are a critical operation that we have to optimize as much as possible. And this requires careful tuning, but also this implies that we have to avoid the extra overhead of additional operations, such as these Hadamard operations that we have just been discussing, right? So in this plot over here, the matrix multiplication in 4-bit will be this blue line, and then the black line will represent the online, let's say, quantization that we have to apply to the input matrices in order to compute our result. So we have to implement this overall idea, trying to reduce such mass as possible the distance between this blue line and this black line, right? And this is something that we just mentioned and we discussed with this last question. And one of the reasons what I mentioned in this is that the Hadamard transform is one of these operations that introduces extra overhead to our method, and we have to carefully tune and also implement in order to reduce this distance or minimize this overhead, right? The Hadamard transform behaves as this normalization that Andrei just described. And if we focus on this Hadamard transformation, the size of this Hadamard transformation is critical if we refer to runtime, right? So when the Hadamard size is less than 256, the problem to solve is memory bound. When it's larger or equal to, well, this depends a bit on the architecture to use, but here in these slides or in these 5090 GPUs, for instance, the breakpoint is it's 256. So if it's 256 or larger, the problem becomes compute bound, and yeah, basically this is the overall result, right? So for Hadamard size of 32, solving this Hadamard transformation as a matrix multiplication, it's just faster because it's a memory bound problem. But when we move to Hadamards of 256, then we have this fast worst Hadamard transform that is able to solve this transformation in complexity on n log n, right? So the time it takes to apply this Hadamard transformation is going to be determined by the time it takes to load our matrices, right? Because it's a memory bound problem. And that means that if we move our data really efficiently, our method is going to be much faster. So that also means that the Hadamard transformation can be hidden in some sense by this matrix loading, right? And we already have to load these matrices because we have to quantize them. And since this is a memory bound problem, that means that we don't necessarily have to apply Hadamard transformation, but any kind of transformation can actually be applied here if we want. So this alpha projection is also memory bound, and we solve this problem with Catalyst fused kernel for Hadamard sizes of 32 that are actually really small Hadamard sizes, but we found that they just work, right? They just work. So we don't really need to use larger Hadamard sizes here to make our method work. So when we refer to this dense Hadamard transform, what we actually have is this kind of block diagonal matrix for a specific group size. And if all these blocks in the diagonal are basically the same, what we can do is to transform this previous problem to this one. And since we are focusing on MXFP4, we can just define this Hadamard size of 32. And that means that instead of applying this 32 by 32 block to each block on this blue matrix, we can just transform this problem to this one, because all the information is contiguous in memory, and that means that this Hadamard transformation can be applied as a normal gem, right? So taking advantage of this alternative way of solving this Hadamard transformation, we have defined a custom Catalyst gem template, right, to execute this in the following way. So the inner dimension, which is this one over here, is going to be fixed to 32, right? And then all the remaining elements are going to represent the outer dimension of this left-hand side input matrix, right? And then we can just define these tile shapes in the following way. In this case, 128 for the M dimension. I'm going to talk about this a bit later, but basically the N dimension and the K dimension here are 32 because it's never going to be larger than that. And then the following configurations just depend on the specific hardware architecture that we are using, such as this MMA shape over here. Okay, so what we have done over here is that we have two BF16 input matrices. One of them is the matrix to quantize, and the other one is the Hadamard matrix. Then we apply this dense Hadamard transformation with this custom Catalyst gem template, and the accumulation of this operation is going to happen on FP32, right? So the output is going to be stored in shared memory. Then what we have done is to define a custom epilogue to produce the following three results. So the first one is going to be the values quantized to this E2M1 format. Then the second parameter is going to be this the scaling factor that I just mentioned in the second slide with this E8M0 format. And the third parameter is the clipping mask that is going to be used in the backward propagation. So this is just a binary mask. And one very important information over here is that this custom epilogue is almost for free, because it happens locally. We don't need synchronizations here because let's say that each thread is going to contain all the information needed because we work with these groups of 32 elements, right? So no synchronizations are needed. We just need to take our information after the Hadamard transformation, compute these output elements, and just write them back to global memory, but no extra synchronizations are needed. Okay, so this previous slide just describes the fused quantized kernel that we have implemented. And right after this, before the matrix multiplication, we had to add an additional method that is this scaling factor rearrangement. This is not related to Quartet or to our implementation. This is just related to these new Blackwell tensor cores that requires the metadata information to be stored in a specific way, that is this layout that I show on the left. And this is going to be applied to the E8M0 scaling factors that we have computed in the previous step. So overall, here I show an example of how these three methods are executed. So this example represents the forward path of our method. So we are going to receive this input and the weights, which we are going to quantize on the fly, right? So this forward quantize method applies the Hadamard and then computes these three outputs that are the FP4 values, the FP8 scales, and the binary mask. Then with these scales, we call this two-blocked function, which is going to rearrange the information to this specific format required by this new Blackwell tensor cores. And then we are ready to call this CUDA's FP4, MXFP4 gem, right? So here I have a performance breakdown for some layers of a Llama 70V model. And here the y-axis shows the percentage of the runtime that each of these three methods take, right? So we can actually see that for larger matrices, the matmul represents an important percentage of this runtime, but the smaller the matrix, the more the overhead of these quantization-related operations. This is not actually related to our implementation. This is just that as we increase the arithmetic intensity, the matmul is just going to take longer, and we can hide these quantization-related operations easily, right? Then I'm going to describe first this figure on the left. Here on the title, you can see that we have used 32 by 32 thread block tiles, and this is related to this slide that I showed over here. So this first parameter is the parameter that we tune to 32 or 128, and this is related to the tile shape, right? The larger this tile shape, the more efficient we can manage this data, and as this is a memory bound problem, this is just going to accelerate the performance of our kernel. And so that's the reason why we increase the performance from this first figure to this second one. And the third one is just adding a Triton MXFP4 rearrangement kernel instead of just PyTorch level, a PyTorch level method. But actually this rearrangement function, as you can see, already represents a minor percentage of the total runtime. One additional optimization that we can apply in the future is to fuse this rearrangement in the fused kernel, right, that all contains the Hadamard and all the quantization related operations. But as it represents fairly a small percentage of the runtime, we didn't invest too much time on this fusion. But this is something interesting to do in the future, because we continue working, as I said, in the optimization of these kernels. So one thing that I wanted to refer to here is this CUDA library that we published like 1 month ago or something like that. And here is this is the repo that is going to contain all the kernels related to Quartet and also quantization related projects that we have for these micro-scaling formats. We already included a bunch of kernels for the forward pass on this GitHub repo, more specifically, not only for this Quartet paper, but also to some PTQ project. And we continue working on optimization on the inference, but also on the backward pass. And we hope to add the backward pass kernels in the following weeks. Here I have some speed up numbers end-to-end for 2 different models. We can discuss them later if you want, but this is the repo where all the kernels are going to be dumped afterwards. And then on the backward pass, I'm not going to go into more details, because basically all these optimization and tricks that I have been talking about in the previous slides can also be applied in the backward pass, because we have Hadamars everywhere as well, and these Hadamars are also memory bound. We just have some additional transpositions that have to be applied on the fly, but the kind of tricks of these memory boundedness are basically the same ones, and we can have also some additional masking functions like this one that we can fuse on the epilogues of our kernels, but as I said, this is still a work in progress. And here I have some speed up numbers for our kernels. On the left, this speed up is of MXFP4 with respect to FP8. On the right, with respect to BF16 for from layers extracted from 3 different models that are, well, the size is this 800 million 70V and 52V, right? We can see that the speed up of the forward pass with respect to FP8 is around 2.2 up to 2.2, the backward around up to 1.5 or something like that. And the difference of the performance of the forward pass and the backward pass, as I mentioned, is that we have invested a lot of time on the forward, not so much effort on the backward yet, but we are working on it, and we are going to release the kernels soon and also improve these results. Yep. And then we already described this figure over here. So I think that's all from the kernel perspective. I don't know if you want to continue to have some questions about this.
So there's a bunch of questions in chat. Like, how much content do you guys still have planned?
We only have a few slides, like some baseline comparisons, and then basically just a recap.
How about we do that, and then we do questions in the end?
Oh, sure. Yeah, then. Yes, so at one point I already mentioned that we can use the effective multipliers from the scaling laws to compare methods that are the same precision, and this paper wouldn't be full without a proper baseline comparison. And to do this, we do exactly that. We pick a bunch of 4-bit methods that were proposed in the recent years for 4-bit training of LLMs or otherwise deep learning models that were adapted for LLMs. And we fit the scaling laws for them. We obtain the efficiency factors, and from these efficiency factors, we can see that the Quartet, the composite method we designed with these sorts of scaling laws in mind, we're using the latest available methods that came out within the last 6 months, beat all of the existing baselines, such as this LQ, Jetfire, Halo, and LSS, and in general, this is the best you can get for 4-bit training at the moment. And one other thing that I should note is that we build our comparisons on top of scaling laws of a very specific thing, that is the validation loss of pre-training of LLMs. And to build a proper comparison of models based on this one number, we need to show that this number is actually consistent with some sort of downstream performance of other performance metrics of LLMs. And here we do this with a number of zero-shot tasks, such as Helaswag, Vinagrande, or Archisi. And basically what we show here is that this zero-shot performance is consistent with validation loss, meaning that the pair-wise comparisons, like which loss is smaller we get from our scalar loss from which we build the optimality regions, actually translate into zero-shot performance. And again, we show it only for the pre-training of large language models, because things like instruction tuning or policy optimization are way outside of the scope of this paper, and mostly depends on some additional tricks or data mixtures that would be selected for those, as opposed to a more simpler pre-training setup where you have usually one data mix and validation loss from it. And here we simply demonstrate that this one validation loss is consistent with some other performance metrics of LLMs, and our comparisons still stand. And to sum up what this paper is about, we proposed a novel method for comparing different quantization or training methods that normalizes the training and inference costs and uses scaling laws to accurately predict performance in terms of accuracy and make an easy compute comparison of different precisions and methods to be able to tell in advance which training method would be the best for a certain training setup, like model size and compute budget. And to do this, we fitted a bunch of scaling laws and demonstrated their robustness. And we also tested our method for pre-training of a model that is way outside of the scope of the models we mainly trained. So mainly we trained models from 30 million up to 200 and actually up to 800 million parameters. But for one additional ablation, we trained an 8 billion parameter model just to see that it still converges stably and that our method still performs reasonably there as well. And I guess that would be all, and we'll be happy to answer any of your questions.
Wonderful. Thank you, Andrei. Thank you, Roberto. I guess what I'll do now is I'll just post the questions on the screen, and then let me know if you can read them. Can you see this?
Yes. So I think this one's for you, Roberto.
What new features would like to see in the future GPU architecture to further accelerate your kernels? Oh, that's a very good question. That's a very good question that I don't always ask myself this kind of question. I just adapt the kind of implementation that we have to the kernels available. One thing that I kind of missed from the previous architectures is this 1-bit support that to some point it's discontinued in these new architectures, at least from the documentation perspective. And then this kind of, for instance, this kind of, I think that these kind of microscaling formats are really important, not only from the kernel perspective, because previously we had to implement them by hand and from scratch. But I think that maybe support these kind of microscaling formats to lower bits can be an interesting feature to support in hardware. Yeah, I don't know what else. One interesting feature will be talking about microscaling formats support other group sizes than 16 or 32, like 128 or even larger. We found that this can be an interesting feature depending on the application. So talking about microscaling formats, I think that extending the support to other group sizes or have in general more flexibility over here will be a very interesting future to have.
I think I have something to add here, that there is this very interesting idea that not for this project specifically, but for some post-training quantization, we had a sort of trade-off that exponentate Mantissa 0 microscaling scales have enough range to cover any quantization, but they're not fine enough. And FP8 microscaling scales are fine enough, but don't have enough range. And maybe one interesting thing they could do in the future is do microscales for microscales, where you have like the kind of the macro scale that has a lot of range, and then you have microscales which are a little finer, and then you have the actual values that are other D-type, and you can mix and match and build a pyramid of it. Yeah, that'd be interesting. So
thank you, folks. I guess like this is another, I think might be another question to Roberto.
Dense gem plus Hadamard Epilogue should be compute bound in theory. I mean, the thing is that here the epilogue is always prologue, not epilogue to the dense gem. So I don't really understand the.
I think this is generally a question about that our method kind of doesn't make gems not compute bound. Yes, it's still compute bound. It's not about the gems itself. It's about kind of the additional methods we build around them, and we're trying to build them memory bound as to not slow down the gems itself. Of course, you wouldn't be able to kind of make gem memory bound because the compute you have to take is still there. It's just everything we try to design around it, we try to minimize the amount of compute you need for it.
Right. This is a longer question from the pool.
Okay, so the easiest way you can see why this happens is, let me open this slide, is that where was it? Here. So yes, why we multiply by one and divide by the other. So imagine if both your training and inference speedups were 2x, then to normalize for inference speedup, you take a model that's twice as large, meaning that your training budget also just grew. Training budget under fixed token count also grew up by 2x, and you have to cut the tokens. But then you have the training speedup that again expands your budget, and you've matched the exact training budget. So actually, this division by forward speedups come from the fact that you actually increased the model size itself. And if your training speedup doesn't match your forward speedup, then you will actually train on less tokens because your model is larger but not as fast on training. So this is just, if you write out the actual costs, that is kind of training budget is proportional to the two, you would see that kind of when you multiply these two, you get exactly n times d times training speedup, which makes sense because you just kind of increase compute exactly by this SP training, but you have to multiply by this kind of. So yeah, if you just do the math carefully, it comes out like this.
Right, and I think this is going to be the last question.
Okay, so this is about some sort of maybe even neural architecture search where you're trying to come up with smarter strategies for quantization, maybe like not quantizing certain parts or quantizing but to higher precision. And in general, what I would say is that it can probably still be described by the same scaling law, but again, if your training setup is consistent, it can still produce consistent losses, meaning that it can still be fit with the scaling law. And we expect that still some sort of capacity would be there, and this form would probably be good for it, but it might yield significantly different effectiveness factors while not changing the total bit width or latency by too much. We haven't experimented with this a lot, but we still believe there would be some notion of capacity in there that you could exploit to use the same comparison scheme we proposed here.
Actually, I lied. I want to ask you guys one last question before I let you guys go. So since you're using Blackwell, I'm kind of curious how come you guys didn't explore like the NVFP4 data format and why you stuck to MXFP4?
Okay, so maybe I can start with this one. So we started this project before anyone actually got the first Blackwell chips, and sort of no one knew like if it even existed and what it would be. And MXFP4 is like a well-documented format for which the specification has existed for a few years, and we just picked the one that made sense, and we did all of the initial ablations and pseudo-quantization. And then when we actually got the GPUs, yes, everyone realized that the MFP4 is noticeably better. But MXFP4 is sort of a more standardized format for which the specification has existed for longer. And it's we're actually looking at getting MXFP4 support in other accelerators, such as some Chinese accelerators or Amazon accelerators. So it's maybe a little more future-proof as well. We'll see about that one.
But I guess your hypothesis is like the curves would maybe go like a bit down or a bit up, but you wouldn't expect any dramatic
since it's sort of a capacity of representations, it mostly depends on like your inner data type, and it's still FP4 is still roughly the same bit width, so we expect it to not change by much. Yes.
All right. Well, I think that's it for me and for chat, folks. If you have any more questions to Andrei and Roberto, please feel free to message them on Discord or shoot them an email. Thank you so much, guys. I really appreciated this, and you're more than welcome to come back again in the future. So it was great having you. Thank you.
Thank you.
Thank you.
Have a good day.